We're now going to look at the area between two different functions. To that end, let's suppose that f and g are the two functions whose bounded area we're trying to find. As usual, we'll start with a picture to help us visualize the mathematics. This ends up being a problem in geometry. I'll draw the area under f in blue and the area under g in yellow. By subtracting the yellow area from the blue area, the stuff left over is exactly what we're looking for, the area between f and g. Hence, we can compute the area by subtracting these two functions. Mathematically, the way that we'll compute this is with the integral of the absolute value of f minus g. Note as well that if g of x is the zero function, that is, its graph is the x-axis, then this is the usual notion of absolute area. The absolute value shows up for two important reasons. The first is that the area bounded by two functions should always be positive. We don't want to assign some notion of negative area in this particular instance. Secondly, we don't want to have to worry about which of these two functions is bigger. If f is bigger than g, then for its area to be positive, we have to do f of x minus g of x and not the other way around. So, if we throw an absolute value in, then the difference is always positive and we don't have to track which function is biggest. That being said, in practice we do actually have to track whether f is greater than g. And that's because in order to get rid of the absolute value when we compute, we have to know whether the integrand, f minus g, is positive or negative. Let's start with something not too complicated and find the area bounded between y equals 1 minus x squared and y equals x squared minus 1. As always, we'll start by giving a graph. This question has a lot of symmetry, which the graph helps us to see. Now, we're not going to take advantage of it in this problem, but if you were to do it, you could. Our first step is to find our bounds of integration, for which we need to find where these two curves meet. We will equate the two functions and solve for x. Doing this gives us x equals plus or minus 1, and if we plug that into y equals x squared minus 1, we get y equals 0 both times. We can put everything then into our equation for the area to get the following. Note that since 1 minus x squared is bigger than x squared minus 1, we can simply drop the absolute value. Simplifying all of that then gives us 2 minus 2x squared, which we can integrate without too much trouble. And here you can see the symmetry manifest algebraically. Again, there's a lot of symmetry here. For example, you could just compute the area of the top half and multiply by 2. Or even go one step further and compute the area of the top quarter and multiply by 4. In this next example, we'll do something a bit more complicated. Let's find the area between y equals x and y equals x cubed. As always, let's make a graph to start. Again, we see that there is a lot of nice symmetry here, but I want to show you how we deal with the fact that x cubed is bigger than x on one half and less than x on the other half. To find where these two curves meet, we equate the two functions and solve for x. This yields x equals plus or minus 1 and 0 as our solutions. We throw this into our area equation, but this time we want to split the integral into the intervals -1, 0 and 0 to 1. The reason for this split is that the function which is biggest changes depending on which interval we're in. So, if we are in -1, 0, x cubed is the bigger function, while in 0, 1, x is the bigger function. This means that we can remove the absolute values like so. Note that the effect of the absolute value is just to make sure that the bigger function comes first, and then we subtract the smaller function. At this point, we just have to grind out the algebra, and again we see the symmetry appear algebraically, but if we do all of this, we'll get an answer of 1/2. Thus, the key to finding the area between two functions is just to subtract those two functions.